Okay, let's begin the seminar. We thank you for everybody that's in the venue, the CHPC lecture room this morning. I think we've got a few people online on Zoom as well, so thank you very much to everybody that is joining. I think it's really for the CHPC an honor to welcome Professor Marc Massot here, and also his colleague, Luc
Guarin. That's right.
Thank you, Luc, for also joining us via Zoom. So they're going to present different parts of the presentation.
Two voices.
Yeah, so Professor Massot is a long-time collaborator of Malebogo Ngwepe that is here. She's at UCT, and of course Malebogo is a long-term user of the CHPC. I mean, so she knows what the CHPC is all about, and I would like to say that she's benefited a lot by having compute access here. So thank you very much for being the link to also now welcome Professor Massot here for a seminar at the CHPC. So I'm not going to read your full bio. I didn't share it, but I made a few observations. I mean, of course, he obtained his PhD already in '96 École Polytechnique. But you made the full circle, I see.
Yeah.
But on the route, you were affiliated with very prestigious other institutions. I mean, Yale University, then you went to Stanford and University of Lyon, and then what is École Centrale de Paris? I suppose that's a different...
Yeah.
And then you came back as full professor to École Polytechnique.
That's right.
And that is where you are currently based. And I think the main summary is his main fields of research are mathematical modeling and numerical analysis of PDEs, partial differential equations, and dynamical systems for multi-scale systems, scientific computing, and high-performance computing. So I've also learned that Professor Massot has been involved in setting up quite a number of computing centers. I think that's even why it's more relevant for you to be here and have further discussions with us. And also applications in combustion, two-phase flows, plasma physics, and biomedical engineering. So we're looking forward to your talk. The title, Towards the New Approach of Mesh Adaptation Methods and its Impact on the Simulation of PDEs. Thank you very much, Marc.
Thanks a lot for your welcome here, for the nice introduction. It's a great pleasure to be here. I'm visiting University of Cape Town for a month, and thanks to Malebogo Ngwepe. So she was kind enough to set up a National Research Foundation funding so that I could come here for a month and interact with her group. We are, in fact, doing a lot of numerical analysis and scientific computing, and mesh adaptation is something that a lot of people have been working on because it's reducing the memory trace of your simulation, allowing you to do a larger simulation with the same amount of computing time. And but as you see along the way, there are a few issues we wanted to tackle on this. So Loic and I are leading a team in the lab that's called HPC at Math. So the principle of that is that we are trying to make the link between theoretical numerical analysis and analysis of partial differential equation, designing new numerical schemes, but also connecting with high-performance computing. So having 4 or 5 people that are really software developers, experts in applied mathematics that can really develop new generation of codes, advanced C++ code, and we are connected to the NUMPEX initiative at the level of the country, which is the equivalent of the exascale computing program in the US, at the scale of France. And the idea is that one of our codes that I will talk about today is involved as a demonstrator in this program. So the idea is to make the link. So to show how it's working, we decided to do a two-voice seminar. The first part is going to be numerical analysis, and the second part is going to be a new data structure that can handle this and go for high-performance computing on a code that Loic has been responsible in developing, which is the Samurai code. So the idea is that the work I'm going to present here is a work that has been done by a lot of people. So it started with a former PhD student that was working on these issues with lattice-Boltzmann method. He did a very nice PhD on explaining that lattice-Boltzmann methods are nothing more than finite difference multi-step method. So using algebra tools, he was able to recast that into the usual framework of numerical analysis. There's a group of 4 software engineers, Loic, Jocelyn, Pierre, and Laurent, who have been involved a lot into coding and developing the code. And this is a long-term collaboration with Christian Thénault. Everything is on, including this presentation, is on the GitHub of the team. So the specificity here, even in France, is that we have at the same time people doing applied mathematics and people doing code development in the same team, which is unusual at the level of our country, where most of the math lab have perhaps one software engineer for the whole lab, and here we have 4 for a single team, which is like unusual. So the idea is that what I'm going to try to provide you with in the first part of the seminar is connecting mesh adaptation and error control. So showing that not only should you think of reducing the memory trace or compressing the data, but also the key idea is how do you ensure that by compressing the data, you're not destroying the solution, so having an error control on what you're doing. So in order to do that, I'm going to focus on a very, very simple problem so that everybody can capture what's going on here. So the first part is going to be on the Burger's equation. Everything I'm going to present here can be expanded into 2D and 3D, so it's not a matter of the dimension. So let's make it simple. You have the Burger's equation, nonlinear scalar equation with the flux that is u squared over 2. You take the Cauchy problem with this kind of solution. Then, of course, because it's nonlinear, the solution is evolving with time, and at some point you create a shock solution, right? So the idea is that in terms of meshing here, you would like to mesh rather coarse when the solution is very smooth, but you want to put a lot of mesh points where the shocks are really being created. So you would like to use this mesh adaptation. So in what we're doing, we're working in the field of, for example, hydrogen risk in nuclear environments. And in that kind of case, what you're doing is you're having a room that is like probably several times this room, and you're taking a look at the hydrogen flame that is deflagration that is propagating, and because of the obstacle is transforming into a detonation wave. You can think of Fukushima if you want for the explosion that's coming up. And so the idea is that when you do that, of course, you're not going to be able to mesh the whole room with the fine mesh that is the resolution you need for the flame propagation, so you need mesh adaptation. So when you do that, there are basically 2 ways of doing this. So one way is to use adaptive mesh refinement techniques that have been developed for many years, but we didn't want to do that because we have a hard time characterizing the error we're making by compressing the solution. So we went for what we call adaptive multi-resolution techniques based on wavelets. So you have a set of nested grids, dyadic grids in 2D here, but can be in 1D, 2D, 3D. And the idea is that instead of just having a kind of a heuristic saying, hey, I have a high gradient here, or I have a high second derivative, so I put points. So here you're going to decompose your solution on a wavelet basis. That's based on the very fundamental work of Ingrid Dobeschi and Stéphane Mala. And the practical approach I'm going to present here has been due to Ami Harten and Albert Cohen, collaborators at Sorbonne University. So basically, depending on the grid you have, you define a projection operator that allows you to go from a finer grid to a coarser grid. So it's just taking the average of what's going on here, with the green one putting the blue one. And then you need the prediction operator that's taking from the coarse grid to the fine grid. So how do you define the solution from the coarse grid onto the fine grid? So you take neighbors here. So here, if your cell is the K1, then you have K minus 1 and K plus 1. And from this, you're going to reconstruct a polynomial. And by taking averages, because it's a finite volume method, you're going to predict what's going on into these 2 green cells. And the idea is that you can define regularity indicators by taking a look at the difference between the actual solution and the predicted solution. And it's defining what we call a detail. And this detail can be analyzed in terms of wavelets. And it's providing you with a way of defining the regularity of the solution. So you can think of that as a Fourier transform, except here it's not like global in terms of the signal, but it's localized in space, right? So you have a frequency analysis or a regularity analysis, but which is localized in space. And depending on the regularity of the solution, your details are going to decrease more or less rapidly. So the idea is that way you can analyze the regularity of the solution on the fly and decide, depending on the details, if the solution is smooth or not. And you can use as the fast Fourier transform. You have the fast wavelet transform. So the solution on a fine grid, L bar on top, is going to be the solution on a coarse grid, L bar under, plus a series of details that are defining how you're going into the more details of the solution. And basically, you can threshold your solution, taking a look at the details and providing threshold here, epsilon, which is the distance that you want to have once you have compressed the solution. So for example, in LP norm, so this guy here, you're going to set it to 0 if it's smaller than a scaled version of epsilon, and you keep it if the detail is big enough. So if it's big enough, it means the regularity is not smooth enough, so you keep the details. If it's smooth enough, you can get rid of the detail and then have a compression of the solution but with a given error. So you know exactly, you're compressing the solution. So it's really like, image processing. So you have a compressed version of your image, and you know exactly, you can reconstruct this version, the version at the finest level. So here, a simple example on this function. So this is the function here. So you have up to 12 levels. So it's a 4096 grid. You have the level that you have here. So that's the area you're making. So basically, by using less than 4% of the grid here, you can represent a function up to 10 to the minus 3 in terms of the L1 norm. And basically, you know exactly what you're doing because you're compressing the solution, but you know to what extent you're making an error by compressing. So that's fairly good. So dividing by a factor of 25 the size of the grid is pretty nice, but you still have a good representation. The key thing here, when you think of that the difference based on the AMR, is that in this kind of situation, you're compressing the solution, but if you're compressing an image, you're never taking a look at the image in the compressed form, right? You reconstruct the image on the finest level. So here's the same thing. You're compressing, you have a grid that is only like less than 4% of the grid, but you can reconstruct anytime the solution at the finest level if needed, so which is a major difference with AMR. So what I've presented here is a static version of the whole thing. So it's like for a function. It's not evolving with time. What we want to do is PDEs, evolution in time. So basically, the idea is, since we're going to use finite volume with a global time step, which is based on the CFL condition, based on the smallest size space step, we're going to have to use dynamic mesh refinement, which is adapting on the fly. So there are two heuristics here that we're using. So the idea is, since there's a limited speed of propagation, we add security cells. So we have a kind of a tree, and we're extending a bit the tree of one cell, so that if the local shock is moving from one cell, it's always in a zone that is refined enough. And what I presented so far was just a matter of coarsening the mesh, not refining. And so here, if you have the formation of singularities, as I mentioned with Berger's equation, then if the details are becoming a bit high, then it means that probably a nonlinear phenomenon is really happening, and the solution is getting steeper, and you need to put grid points. And if there is another scaling function with a regularity index, then the idea is that basically you're going to add cells. So here you have a viscous Berger. So that's the solution at the beginning, like a Gaussian function. And then when the shock is creating, you're going to add grid points to follow exactly where the shock is really moving. So the idea, if you're using finite volume, there are versions for this in terms of finite difference too, and point wavelets, but I'm not discussing that. The idea is that if you have a grid like that, and suppose you want to evaluate for your finite volume method using a Godunov flux, you have to evaluate the flux at this point, right? So the idea is that since you have the solution on this side, the solution on this side, how do you calculate the flux? So the idea is you're going to build a Gauss cell here at the same level. So, for example, if you have a Riemann solver, you're going to have the cell on this side, and you reconstruct the solution by the prediction operator, and it's going to eventually be a recursive process because you don't always have all the solutions at your disposal. And then once you have this cell here, if it's two cells as if you were on the same grid, so you calculate a flux that is based on your usual Riemann solver or approximate Riemann solver. It's going to be a Godunov flux here. So you're pretty much okay. So you evaluate the flux at this level. I remind you that if the solution is smooth, this is one level where we approximate the flux, but the finest grid could be way above, right? It could be a much finer grid because that you're not using because the solution is smooth. So if you do that with the Berger's equation with the sine function, that's pretty much what you get. So using a first order method, so you're adapting the grid. And the idea is that you were doing all this business with the wavelets to have a very precise solution. And you can see here that it's a bit of a disaster, right? So it's really smoothing the solution out. And it's not predicting the right location for the shock. So something is kind of wrong. So that's something we did for a course. And we realized that something is wrong. And we wanted to analyze this. By the way, for a lot of people that have been doing this, like Godunov methods and system conservation laws, are coming from the astrophysics community. And in that community, what they usually do is this AMR based on what I've just described. And they're using like first or second order methods. So it's really what's happening here. So the idea is that we wanted to do a numerical analysis and explain where this what's going on with this problem. So the idea is that I'm shifting here for the Burgers equation to a very simple linear equation in 1D. So it's just transported by a constant velocity that could be extended in 2D and 3D. And Thomas did something like that in 2022. So I'm going to have the same grids as before. So I remind you that U is the exact solution. V is going to be the solution on the finest grid. So you define a fine grid on which you would like to have the solution. And you define fluxes that are based on a linear approximation, combination of the values of the function. And you know that if you're using this kind of flux evaluation, you can do what people call modified equation. So the idea is that you're using a Cauchy-Kovalevsky procedure that was done in several papers. Basically, you can show that this kind of equation, the upwind scheme, is a first-order solution of the transport equation, but a second-order solution of an equation where you have added this diffusion. So that's what we call usually the numerical diffusion. So it's a first-order scheme, and you can characterize to some extent for smooth solution how the scheme is smoothing the solution through Laplace operator. If you do a Lax-Van der Waals scheme, second order in time and space, then same thing. You have a modified equation that tells you that you can have a dispersive term this time. So basically, and you have some coefficient that is related to the CFL number in your problem. And if you go third order, which is, for example, one-step monotonicity preserving scheme or third order. So if you're not familiar with that, it's the direct extension of Lax-Van der Waals methods for third order. It's preventing the use of Winnow schemes with the Runge-Kutta 3 method. And it's much more compact because it's going high order in time and space at the same time in the same cell. And so that's the same thing. We have a fourth order operator here. So this modified equation is something that is known, is a very classic way of doing things. So we wanted to see if that can be used to characterize the error we have, but including the mesh adaptation, the fact that we're describing solution at different levels. So now we're going to introduce a reconstruction operator with S hat being either S, which is the number of neighbors that you have to do for the prediction operator. So that means that if S hat is S, it means that you're going to reconstruct the flux at the finest level of the solution. So you're eventually at a different level, but you're reconstructing at the finest level. If S hat is 0, it means that you're directly evaluating the flux based on what I've shown before, which is the current level, which is not the finest, but the current level where you're playing. And so if you're doing the same like modified equation analysis, so remember U is the exact solution, V is the solution on the finest grid, and W is the solution on the adaptive mesh. So if you do that, the idea is that what you can have is have a modified equation. So now that's the original modified equation. And now using multi-resolution analysis, if S hat is 0, then you realize that it has a bit of the same form, except that the 1 here is 2 to the power delta L, which is the difference of level between the current level and the finest. So if you have a smooth solution, it means that you are adding a huge amount of numerical dissipation, numerical diffusion into the system. And if you take S1 equal S hat is 1, it means that you're reconstructing the flux at the finest level. And in that case, you recover the usual expansion with the main term being only diffusion. So that's quite interesting. And it's the same if you go second order. So you have the original one. Now, if you do the flux evaluation at the current level, which is what people in the AMR are doing, then you get this diffusion operator. So it's the main term is completely different than the usual dispersive term. Whereas if you do the flux evaluation at the finest level, you recover the same like main term of the expansion being this dispersive term. So the idea, I don't want to bother you with two theoretical results, but the idea is that we could do a theorem where we can analyze the exact error that you're making between the exact solution and the solution on the adaptive mesh, which is the sum of 3 errors. So you have 3 components. One is the delta x to the theta, which is the usual mesh on the finest, the usual like error of the scheme on the finest mesh. So that's if you're using the finest mesh, that's the error you're expecting. And then you have 2 errors coming from the mesh adaptation. One is really what we call the prediction error. So it's basically at what level are you estimating the flux, and it's 2 S hat plus 1. And there's an error. You remember that you're thresholding all the time based on regularity of the solution. So you're changing the mesh all the time. So it means that for every single step, and the number of time step that you're making is the final time divided by lambda delta x. So that's the number of time step that you've taken. The finer the mesh, the more time steps you're making, and the more thresholding you're doing, because you're doing thresholding at every time step. And so you have three errors. So the idea is that you have the discretization error, which is the one that you were expecting, the perturbation error based on the prediction operator, and the thresholding error. So the idea is that if you're in the case where basically theta, which is the order of the scheme, is smaller than 2s hat plus 1, so it means that to some extent, in that case, that's pretty much okay, because you will not see this perturbation error. So the prediction of the flux at the finest level, for example, in the case we were showing, would be quite okay. If that's the first example, you have this term, then it will add some error in your system, and that's what we've been seeing before. And that's the difficult case. If theta, for example, is second order, but this guy is only 1, then it means you're going to get a huge error coming from the prediction operator, from the perturbation error, and that's going to some extent destroy your solution, and that's what people have been doing in AMR structures. So now that you know what's going on, the key thing is that we have to explain how to compute the fluxes at the finest level to have S hat equal 1. So the idea is that you have several levels. So the level where you're playing is this one, and you have a cell and fluxes that you have to evaluate on both sides, right? So the idea is that when you're doing that, you would like to be able to calculate the flux at the finest level. That means you remember it's multi-resolution analysis, so you can reconstruct the solution at the finest level. Of course, if you reconstruct the solution at the finest level everywhere, you're losing the battle, because it's like in terms of memory trace, you didn't do any progress. So the idea here is if you have these 4 cells, by using the prediction operator, which is just a linear transfer, so multiplying by a 4x4 matrix, you can evaluate these 4 guys, these 4 guys, these 4 guys, these 4 guys, just multiplying by the same matrix several times. And then you can just evaluate the 4 cells that are around the interface where you want to evaluate the flux. And you're not evaluating the flux everywhere, but just where it's needed. And so you're doing that for the same thing for the cell that is just on the side here. So with five cells here, you're able to predict the flux using the solution at the finest level, which can be quite different from the solution relying on the average that you're dealing with. So it's a much finer description of the fluxes. And by the way, this is the way fully adaptive multi-resolution was thought of by Amir Harten in the original papers. He didn't want to compress the solution. He was just evaluating the flux only where it's needed. So I'm just showing a few results, and be quick because I want to leave time to Loic to give the presentation on the code. So here, if you take a look at what's going on with a uniform mesh, so that's what you get. So remember, this is Berger's equation. Now we switch to the full nonlinear case. This is the sine function that we've seen before we're reaching the shock. So that's the first order that we expect. If you're doing mesh adaptation and using the flux at the current level, that's what you get. So it's a much larger error. The number that you see is the compression level. So it means here we're using 4% of the mesh. So that's what we wanted to do. But you can see that adapting the mesh and having this kind of error level is not acceptable. So basically it means that if you didn't pay too much attention to this, you have destroyed the structure of the solution. And now by using the flux at the finest level, not only do you compress the solution, but you're recovering the proper error. So basically you're compressing the solution, but having an error control as if you were on the finest grid, which is exactly what mesh adaptation is about, right? You want to compress the solution, but not to lose too much based on the solution on the finest grid. So with that, we were pretty happy to see what's going on. So I'm not going to the details. We can do that for like different cases. And for example, if you take epsilon 10 to the minus 5, you see that it seems you're getting better in terms of precision, but you realize here that instead of having like high numbers, now the mesh is really bad. So you're having a mesh that is really not compressed. And if you want to explain what's going on here, that's what's happening. So you have the Berger's equation seems to be quite on top on the right solution. But if you take a look at the mesh, and that's something that's appearing quite early in the solution, right? So you have something where if you take a look at the mesh, the refinement of the mesh is really bad. You can see that you're switching from one level to the other all the time. So what's going on here? Basically, if you calculate the flux at the current level, the flux is really wrong. And since you have a multi-resolution with a very small epsilon, you can capture high frequency. So the flux being wrong is creating high frequency waves that are propagating all over the place, and you're meshing that. So you're resolving these high frequency waves that are coming from the fact that your local flux is quite wrong. So in terms of mesh adaptation, this is a nightmare, because in terms of the data structure, you're switching from one level to the other all the time. In terms of cache miss, that's going to be crazy. So here, if you're doing adaptation at the finest level, that's what you get. So basically the mesh is quite nice, and in that kind of situation, you're really compressing a lot. And you can even take a look at what's going on here, showing that basically the error that you're making would be quite large, because it's 10 to the minus 5. You have a large error when you're having the mesh, the evaluation at the flux at the current level. Now, if I'm taking a look at what's going on in terms of the multi-resolution, that's the error that I get compared to the uniform mesh. And you can see that putting 10 to the minus 5, I have even in L infinity norm, I have a clear picture that the difference between the solution on the finest mesh and the solution with the compressed mesh, they're okay up to that factor, 10 to the minus 5. I have error control on my solution in space, whatever the time. So that's pretty much nice to have that. The idea is that we are finalizing the paper. These are very recent results. And the idea is that with order 1 or order 2, that's the case I was presenting before, the prediction operator has to be high order 2 so that we're not losing what we do with the first and second order method. If we go for third order, the scenario is a bit different, because the idea is that now, since when I'm going to level 12, the idea is that, you remember, I'm doing an error that is relating to thresholding, so it's the multi-resolution error. And since I'm having a lot of time steps, at the end of the day, the main source of error is this guy. So the idea is that I cannot really get rid of this, or I could take epsilon 10 to the minus 5, so I'm getting closer to the finest solution. But still, by using the prediction at the finest level for the flux, I'm doing something where I can really just decrease the error that I'm making. And once again, the regularity of the mesh, if I'm using the flux at the current level, I'm doing a job which is okay, but I'm switching from levels to levels, and that's not good for the solution. And I cannot control, it's 10 to the minus 4 here. I'm not controlling what's going on in terms of the multi-resolution analysis. If I'm switching to flux at the finest level, I can recover a very smooth version of the grid that is predicting, to some extent, a solution that is really 10 to the minus 4, so I can really handle the error that I'm making with the mesh adaptation. So take-home message, I have a way with the multi-resolution analysis by calculating the flux at the finest level to do mesh compression, but still have an error that is completely defined by the epsilon that I'm providing as a user. And here you can see the difference between, so there's 1 order of magnitude between for this third order method, there's 1 order of magnitude of difference. So I wanted to present this in a very simple case of Berger's equation. Of course, you can use that in a very more rich environment. So this is a 2D Berger's, so I'm not sure if it's showing quite well on the screen, but the idea is that here you have a mesh that is like oscillating a lot, whereas this one is kind of perfect because you're having the flux at the finest level, and you're not, for the Berger's equation, same thing, you're not solving correctly the solution. We have extended that to Euler 2D, so this is the Balsara-Shu vortex, so it's a supersonic vortex for Euler equation that is traveling along the diagonal. So in that case, you can do a very nice job in terms of predicting what's going on with the flux at the finest solution. So it's really reproducing, so it has crossed one way, and we have a solution that is quite nice with the third order solution. And that's the case that we've been working on. So this is a contact wave. That's a shock that is coming back bounced from the top here. So it's hydrogen simulation with the complex chemistry and detailed transport. You have a shock boundary layer interaction that's taking place here, and the detonation is going to start here with complex chemistry, and this detonation is going to travel and interact with both the contact and the boundary layer. And that's something we're doing for the hydrogen risk with the people at CEA, and also predicting the flux at the finest level. And so as a conclusion of this first part, Loic, I think I'm doing quite okay. So we were able to provide a numerical analysis. So I think this is important because a lot of people have been doing AMR, and not being quite aware of what's going on in terms of the error that has been introduced with first and second order methods. And even with third order method, it's also quite a gain to do this prediction at the finest level with multi-resolution analysis, so we can really control the error. I focus today on the convection operator, so only on the convection part of the operator we are dealing with. In the previous simulation, of course, there is convection, diffusion, and reaction, and we extended this currently to reaction diffusion. There's a PhD starting on this issue, and so something you could ask is that in the community, people have been using lots of ways of describing these data structures for AMR, and pretty much every single way of doing this has its own data structure. So we wanted to have this data structure that is able to represent all the ways of doing AMR. So that's what Loic is going to present next. And also something that I didn't have the time to go into the details here. When you start having convection, diffusion, and reaction, you would like to be able to couple all these operators. And we've been designing either operator splitting techniques or implicit-explicit scheme that I don't have time to describe here. But if you're interested, we can chat around this. The floor is yours, Loic.
Okay, thank you, Marc. So this second part is dedicated to Samurai, which is an open source software developed at the HPC math team that provides the computational framework behind the experiments Marc just presented. So the core of Samurai is, as Marc said, is a new data structure designed to represent adapted Cartesian meshes and to navigate efficiently between grids. So for parent and child operation or ghost cell selection, for example. So before going into the details of the data structure, maybe it is useful to show you the approaches found in the most widely used open source software for Cartesian mesh adaptation. So you can find two main families to describe adaptive mesh refinement. The first one is called patch base. So as you can see here, the mesh is represented as a hierarchy of rectangular grids. The main advantages of this data structure is it's a very compact representation. Each grid is fully described by one corner and the number of cells in each direction. And storing the data on a rectangular region also provides good memory locality and efficient cache use. You can also find neighbors easily by checking whether two boxes intersect. So it's pretty nice. But the drawback is that more data is stored than strictly necessary. Due to the grid hierarchy, you have to store all ancestors of a cells defined at the finest level. And since you take a rectangular region, you add more cells than needed. The second family is called cell base. There is no hierarchy, and all cells exist at the same level. So you only have the cells that are actually needed for the computation. The downside is that the mesh information must be stored as a tree data structure. And maybe you know that traversing a tree can be costly. So in practice, the mesh is ordered using a space filling curve, which brings neighbors close together in memory. However, large memory jumps can still occur at the boundary between sections of the curve. For adaptive mesh strategy, you also have two main families. So the first one is what we call the AMR, adaptive mesh refinement, where you use a heuristic criterion, typically based on a gradient or second derivative of one of the fields. This gradient, this criterion drives the refinement and the coarsening. So the weakness of this method is that the criterion depends on the physical problem and may produce more cells than strictly necessary. And the second strategy is so the miniaturization analysis presented by Marc in the first part of this talk. So you have a wavelet decomposition that produces a detailed coefficient, and from this coefficient you can know where the solution is under-resolved. And so this coefficient drive cell stacking in a way that you guarantee the control error between the adapted mesh and the equivalent uniform mesh. But there is some disadvantages from this method. The cost is that many ghost cells are needed to evaluate those coefficients because one of the problem is that you have to project the solution on the level below. So you need more ghosts than just those needed for the numerical scheme. And the refinement kernel is more expensive than a simple gradient threshold. So if I resume, we would like to find an ideal data structure which combines the strengths of both families. So good data locality from the patch-based approach and the minimal cells count of the cell-based approach with enough flexibility to support error control adaptation. This is the motivation behind Samurai. So the data structure represents the mesh using intervals. I will detail that just after, which provides a compressed view while keeping memory contiguous along one spatial direction, just as you can have on a uniform mesh. The cells can be found quickly from spatial or level-based criteria, and the structure is expressive enough to implement a wide range of numerical methods. So how it works? So let's consider this two-degree example with 3 levels of refinement. The fundamental element of Samurai is, as I said before, an interval. So it's like a contiguous range of cells along a direction. And this contiguous range is described by a lower bound called start and an exclusive upper bound called end. And we have also a third parameter called the offset, and is used differently depending on the dimension, and I will explain later. So to build the representation, each level is scanned row by row, and for example, for the level 0, the first row contains 4 contiguous cells, and at the bottom you have for the level 0 or even in the cells you have the numbering of the cells for the x in the x direction. So you can see that the first row contains 4 contiguous cells, which gives the interval 0, 4. And you can do the same process row after row and level after level. So you can see the list of the x interval for each level at the right. The x interval alone are not sufficient. The y coordinates must also be recorded. So for each level, the set of y values that contain at least one x interval is itself compressed into intervals. So as you can see, for level 0, for example, you have an interval for each y. So you have 4 y values contiguous, which give you again the interval 0, 4. And you can apply the same compression at every level. Okay, so knowing which y value exists is not enough because you need to know which x intervals associated with a specific y value must be what x interval is for the y value. So this is the role of the offset array. So it stores for each y entry the start and the end indices into the x interval array. It's important to note that the end indices is once again exclusive. So if I take an example for y equal 14 at level 2, you can see that the offset array indicates indices 2 to 3, pointing to the single x interval 14, 16. It's also important to note that I show you a 2D example, but this structure is fully recursive and is generalized to any number of spatial dimensions. The last ingredient of SAMY is what we call set algebra on intervals. So typically when you want to solve a PDE on an adapted mesh, you have to describe a spatial scheme with a stencil. And for that, you need some ghost cells on either side of the leaf cells. And these ghost cells must be identified and populated before each time step. So one approach is so here I have added the ghost cell for a stencil of size of length 1. And if I just want to store the ghost cell explicitly as a separate set of interval, you can see that the result is a large number of small and scattered intervals. So the mesh is no longer compact, which defeats the purpose of the compressed representation. Maybe a better approach is to store the union of leaf cells and ghost cells together. This combined set turns out to be at most as large as the leaves only set, because you merge ghost cells with a neighboring leaf interval. And as you can see, the mesh remains compact. Okay, so if I take this representation, I need to go back to the ghost. And you can see that the ghost cells can then be recovered on demand by computing the set difference between the combined set and the leaves. And this is one instance where the set algebra is essential. So it allows any subset of the mesh to be expressed and computed without storing it permanently. So in some way, we provide several operators for the algebra of set. So intersection, union, difference, translation, and projection. But if a user need to introduce a new one, it's quite easy to do it. So now I would like to show you how it works in some way. So at the first example, we consider finding all cells at one level that are adjacent to a cell at a cursor level. This is what is called a level jump, and it's useful to populate the ghost at the level 1, for example. So the corresponding set is constructed by translating the cells at the final level. Then we project the result onto the cursor level, and we intersect with the cell at that level. And if you look at the SAMY code on the right, you can see that this is a direct translation of what I said before. Another example is the projection operator that we used in the materialization process. And so the goal is to find all the cells that have a parent at the level above and compute their average value. So the set is obtained by intersecting the cells at a given level with those at level +1 and projecting back onto the base level. So you can describe the set in some way with the intersection of the mesh level and the mesh level +1 projected on level. And then you can invoke a function which is called only if the set is present in your mesh. And what it is important to note, it's that you can see that the formula giving in the Prof set is exactly the mathematical formula that you have on the left. So it's quite easy to read. So a natural question is whether the interval-based representation is actually compact compared to existing approaches. And for reference, a comparison was made against P4S. This is a widely used tree-based library. And we do that on standard 2D test cases. So the result here shows that if you look at the level at 14 refinement levels, you can see that SAMY uses about 1 megabyte to store the mesh, while P4S requires 2.6 gigabytes. So a factor of roughly 700. Beyond the memory saving itself, this compactness has a practical consequence in parallel computation because each process can afford to hold a copy of its neighbor's meshes, and this idea simplifies communication and load balancing considerably. We also have I show you here the main idea of the data structure in Samurai, but it's just the foundation. Samurai also provides a set of higher level tools that make it usable for real applications. So we have a unified loop API which allow to iterate over levels and cells without exposing the underlying index arithmetic that I showed you before. And we have also a simplified access operator to read and write field values directly. And field values can also be reconstructed at any spatial location, as mentioned Marc in the first part, even if the corresponding cells is absent from the current mesh. And so this is needed during refinement and coarsening. We also have some helper classes to assemble complex meshes. We are also able to build explicit and implicit numeral schemes. So we can assemble matrices using PETC on an adapted mesh. Adapted mesh. And we also be able to construct n-dimensional operator and expression using extensor or eigen. And finally, we also have MPI parallelism and HDF5 output for in some way. So based on that, so you have the core part of SAMY is of course intervals and algebra offset, but we also have several containers present in SAMY. So I mentioned extensor and eigen, but we also work on a Cocos containers to be able to run SAMY on GPU. We also tried to develop efficient parallel backend. So I mentioned Cocos, but we would like to use other tools. And another layer of SAMY is to construct a numerical scheme several numerical scheme family. So the first part was about finite volume, but we also work on the Lattice-Boltzmann method, and in September on discontinuous Galerkin methods. We also develop another tools at HPC Atmat team called Pogno, dedicated to time scheme, so IMX method, range equata, explicit and implicit, stuff like that. And the last layer is a dedicated application. So we have many of them, and I will discuss about that just after. Samurai is maintained by 4 core developers with support from a broader community of users and contributors, and through several research programs and institutional partnership. And on the application side, the library is already in use across a range of scientific domains. So, as mentioned on the right column, we work on interfacial flow simulation, on simulation analysis on the hydrogen risk, plasma discharge simulation, lithium battery simulation, combustion, and code coupling simulation. Here are a few examples which illustrate the range of application. So at the top left, you have an example where we solve Navier-Stokes equation on a grid, and on the other we move ink from the velocity field of the Navier-Stokes equation. So these two grids are coupled, but the adaptation is different on both. And since we are able to compute a value of a field on a cell, we can use the two different grids easily. You can also see on the human body a demonstration to handle complex geometries defined by OBJ or STL files. At the top right, you have a simulation of a Riemann problem using a Lattice-Boltzmann scheme. And at the bottom left, we have an example that you can find in the Pablo framework, which is another AMR library. And so the idea is to simulate bubbles, but there is no numerical scheme here. The bubbles just move using a sinusoidal curve. And the last example is a 1D plasma simulation, where most of the physics happen at the boundary, and you can observe here that the adaptation works perfectly. And across all these cases, the same data structure and set of tools are used. So Samurai is an open source software and available on GitHub. So contribution, bug reports, and collaboration proposal are welcome. And the library is designed to be accessible, so anyone interested in testing it on their own application is encouraged to contact us. And thank you for your attention.
All right, almost on time.
Yeah, perfectly done. Thank you very much for this presentation. Before we say anything else, I just want to check whether there's some questions maybe from the room. Charles, you're welcome. Benjamin, you can just check. I don't know if there's questions on Zoom. But Charles, please go ahead.
So my question is actually involved from the book there as well, because this is the link up. So I'm curious to know, how are you implementing this together?
The idea is that we're not yet at the level of implementation. The one thing that we're working on with Maliboho is working on mathematical modeling of clot formation. And so the idea is that we've had, I didn't present much on this, but we've been working on interfacial flows. And the way we've handled that is not solving the jump at the interface, but using diffuse interface modeling. And so people have been doing that with like different ways of doing it, but we have a little bit of experience in that field. And so the idea would be to use phase field models and do an implementation of the interfacial, the clots, the interface between the clot and the blood as being like a diffuse interface where you solve like a coupling between incompressible Navier-Stokes and Brinkman equation in the porous medium. And so we are designing the equations so far. So having the two key issues are thermodynamically consistency. So having something where all the phenomena are designed to be dissipative, and so having like thermodynamical consistency. So it's on the way. I think I can say that we're not far from reaching the point where we want it to be. And then the idea is that going for fast prototyping in Python, just 1D code to check that the method can be handled with the usual schemes. And we have a postdoc that's ready to implement that in Samurai. So the idea would be, that's what we do usually before going to like more involved. I do that a lot with not sure if you know, ONERA is the equivalent of NASA in France, so it's the national French agency. They have a lot of, like, for example, codes for interfacial flows, two-phase flows in rocket engines and stuff. So the idea is that when we design new models or new numerical methods, first, we don't want to go into like very complex codes where we're not sure exactly how the implementation is being conducted. And it could be flow in the system. And if there's a bug, we don't know where it's coming from, either from the method or from the code. So we first do an implementation on Samurai and then show that everything that we have in mind in terms of modeling and numerical methods is really working within the framework of the code. And then once we have this kind of good test case, then we switch to the industrial code. So I'm not sure if so the idea would be to start, first step was mathematical modeling. We are not far from being done there. And then there will be high performance computing on doing like cloud formation with this kind of model that is thermodynamically consistent and doing like 2D, 3D on this. So I'm sure at some point like computational resources will be needed.
Thank you. Any more questions? Nicolette?
Sorry, I totally misunderstood the whole thing, and I come from applications and
Sure.
a regular grid. So if I could this be used offline to take a really high resolution data set and compress the data? And then, or is it more for the online sense as you're running, you're adapting the grid and just keeping resolution where you need it? But then, isn't that just more extra calculations? What's the...
Yeah, that's a very good question. So if just to be sure that I understand your question, what you're saying is that, is it really worth it putting all this machinery on? Well, in most of the time, the answer is no. For example, if you do turbulence modeling and you're resolving like multi-scale where all the scales are present everywhere all the time, if you're doing mesh adaptation, you're going to like gain a little, like few percent of the mesh, but you have to go finer mesh pretty much everywhere. So that's not going to be worth it compared to going straight for the finest grid, right? So in that kind of a case, there's no reason in using adaptive mesh refinement on this multi-resolution analysis. There are cases, though, where that's required. As I was mentioning, if you want to see how a flame in a like mixture of hydrogen and air, how a flame is propagating in this room until that point to that point, of course, you're not able to mesh. The thickness where complex chemistry is happening is 1/10 of a millimeter, right? So if you have to mesh that in the full room here, that's beyond what you can do. So that there are situations where you have fronts or where the real action is really taking place in a very small region of your computational domain. Then, of course, mesh adaptation is able to provide you with something where you're really just changing the size of the system. So let me give you one example where it's really a game changer. We're working with people doing biomedical engineering, modeling stroke in the 3D geometry of the brain. So you do MRI, and then you're trying to see where the damaged brain, how the ischemic stroke is propagating in the 3D geometry of the brain. So 3D geometry reaction diffusion system with like 21 species, like a complex chemistry, complex biomedical chemistry. You cannot run that on a single machine because it's a 3D problem. If you would do that on the finest mesh, you would have to do that on a cluster. So we were doing that with people in a hospital, and there by adapting the mesh and doing also numerical schemes that are able to do that very quickly with the mesh adaptation, we were gaining, in terms of degrees of freedom, we could divide by a factor of 20 the number of degrees of freedom, and we could run that on a workstation and very quickly. So the idea is that there are two cases where you can really gain in doing that. So there, the idea is that it's just propagation of a front, and depending on the geometry, either the front will die, so the stroke is stopping, so the person is happy, or the geometry is such that the front is really expanding, and so in that case, the stroke is really propagating in a large region of the brain, and it's catastrophic. And so even if we're not providing the people in the hospital with a sure diagnostic, it's just something to help, to see what could happen. So you're starting with the MRI, then doing the mesh at fine scale in the different parts of the brain, and you're igniting this reaction diffusion system with algebraic equations. So I'm not sure if I'm responding to the question, but I'm not saying that this is useful for everything. It's just useful when you have very tiny, very strong fronts that are only locating in a very small part of the domain. For example, when you inject liquid in a combustion chamber, liquid fuel in a combustion chamber, the interface is only in a very small part of the domain. So adapting the mesh and getting a very right sense on how this is going to be deformed and creating a spray of droplets, which is going to evaporate and structure the flame afterwards, is critical. But you don't need this kind of resolution everywhere. It's just near the interface. And in that case, adapting the mesh is a key issue. And that's what people have been doing, but not always taking care of the error control. So for example, we have a lot of connections with the Lawrence Berkeley National Lab in the US. And so what they're doing an interesting strategy, but they're not doing accuracy control in what they're doing. So they're doing nice simulations, but it's hard to know if they're really capturing the details of the dynamics in what they're doing.
Yeah, thanks. Is there online any questions? Okay, Charles.
So just to tie back to what Colette was asking, her field is Earth systems modeling.
Oh, yeah.
Have you got any examples from that field, ocean or atmosphere?
No, I'm not. We don't have yet. No. We're not expert in that field.
So what clouds are you talking about? That cloud of when you stab someone and that goes everywhere.
So.
Yeah. So thank you. Actually, the questions asked, I also just had an observation. I'm no expert in mesh definitions and how you implement it, but certainly for me, I can appreciate you addressing the age-old issue of increasing resolution and accuracy, but keeping the computational demand intact. But I mean, the questions that you, or the example you spoke about, also address the question, where is it most applicable? I think you explained it well. So for me, it is certainly a very interesting talk. But I also wanted to check, so how novel is this? I mean, the dynamical mesh resolution as you go along. I mean, is it? So you're writing the papers.
So it's a good. So let me try to give you a flavor on this. So the question of changing the paradigm in calculation, so switching from something where you do adaptive mesh refinement and going from multi-resolution analysis. So this has been present for quite some time in the math community on very simple systems. So systems of hyperbolic partial differential equation systems. So people know how to do that. There were even some error analysis in the 2010. So it was there 15 years ago. People knew how to do this. So in terms of mathematics, they were doing that on a nonlinear error analysis. And what's new here is that we have shown that the critical issue is not what's going on in the nonlinear part where shocks are really happening. The key issue, you can do it with a modified equation in a very smooth part of the domain. And that's where, because you're coarsening the mesh in that area, evaluating the flux properly is critical in that zone. So in terms of numerical analysis, I think that it's fairly new. This idea that it's not a nonlinear hyperbolic system of equation stuff, and switching to diffusion, to the diffusion operator, we even have the same issue that has not been observed, because people think that because it's diffusion, I mean, the Laplace operator is going to help us anyway. So, but it's the same thing. We have to do something very special to preserve accuracy. So in terms of math, I think that's fairly just completely new in the landscape. In terms of mesh adaptation, the one thing that there are two things that are new. The one thing is the data structure. So people have been using AMR for, I don't know, Masha Berger that I met usually at NASA has been doing that for, in beginning of the 80s. So it's not new. But the idea is that people have been using that for years and using always the same data structure for block-based or patch-based AMR, cell-based, and it was kind of all the way down. And I mean, they were doing massively parallel simulation. Everybody was kind of happy with what's going on. So the data structure were not changing much. The reason why we got frustrated is that if you want to compare codes and have an idea of to what extent codes are really competing for a given time to solution for a given problem, it's kind of hard because, of course, the time to solution depends on the data structure you have at hand, how you handle it in MPI and how you're distributing and stuff. And so we wanted to have a single data structure that handles AMR all the way around and also multi-resolution analysis. So comparing these codes was difficult because they had different data structure for multi-resolution analysis only with some very simple cases in math. And in the applied community, there has these huge codes like AMRX at Lawrence Berkeley. We're working with them. So the idea was that changing the view on the data structure. So in the AMR community, they like that because it's a fresh view on, dealing with things. So that's the first point. And the second point, I think, which is important, is that it's combining something that appeared like 2015, the idea of doing like error control and what's going on for more complex applications, but switching to high-performance computing. So,
very interesting. Thank you very much. Let's thank both Marc and
Thanks a lot.
online for this seminar. Thank you. We had, I think, around 20 people online, so we are very appreciative, of course, of the online participation as well. Thank you very much.
Thanks a lot. Yeah.
Thank you. That is it. We hope to do more of these seminars, of course, in future, so we will send the notifications. Thanks to everybody that attended.